Welcome to Study Loop.
In this problem, we're going to use this formula to determine the changes of entropy in these processes. And we're also going to need a latent heat of freezing of water here, which is this value. And so now we can start with part A. And we need to figure out the heat flow into the ice. And so the heat flow into the ice is equal to the mass times the latent heat, which is equal to 0.35 kilograms. These values are given in the problem. And then LF is given here as 3.34 times 10 to the fifth joules per kilogram. And the result is 1.17 times 10 to the fifth joules. This is what goes in for Q, and it's positive in this case since heat is entering the system. Now T is also given in the problem, and it's 273 Kelvin. And keep in mind, we do have to use Kelvin anytime we use this formula. If you're given the temperature in Celsius, you must convert to Kelvin first. And so delta S is 1.17 times 10 to the fifth joules over 273 Kelvin. And the result of this is 429 joules per Kelvin. So if Q is positive, then delta S is positive, and that's what we got here. For part B, we have the same heat except as opposite sign, because now it's leaving the system that we're concerned with in part B. So it's negative 1.17 times 10 to the fifth joules, because this is the heat flowing out of the source. And the T is now 298 Kelvin. That's 25 degrees Celsius converted into Kelvin, which is what the large body of water is at. And so delta S is equal to, again, Q over T, and then plugging in these values gives negative 393 joules per Kelvin. And so since Q is negative, delta S is negative. So this system actually lost entropy, and the other system gained entropy. And part C is concerned with the overall change in entropy. And what we do is we take this change in entropy, and we add it to this change in entropy. When you do that, you get a total change in entropy of 36 joules per Kelvin. And notice that this is positive, as the second law of thermodynamics tells us it must be.